All right, section 5.1, we were taking a look at integer addition and subtraction. We had left off with subtraction, and I believe we had looked at one model, the chip model for subtraction. There it was, right here. Does that look good? Mm-hmm. All right. So we're going to do the equivalent of the chip model, but the charged fields model. And it looks very much the same. It has the same sort of principles. It just draws it a little bit differently. So the charged field model says that I start my circle with, not that big. Hang on, let's try that again. I start my circle, my diagram, so that it has 5 in it, 5 positives. So I have 1, 2, 3, 4, and 5. And I'm supposed to take away, and this is telling me to take away 3 negatives. And the problem, of course, is there aren't any negatives in my circle to take away. So I've got to put them in there somehow without changing the fact that this has 5 as its value. So I'm going to show it just a little bit differently than last time. Basically, what we're going to do is we're going to put these in pairs. I put in a plus and a minus. They cancel each other out, so this circle still has value 5 inside of it, right? But there's only one minus in there, and I need to have 2 minuses, so we're going to add another pair of a plus and minus. And then we're going to do it one more time. I now have 3 negatives that I can take away. So these 3 negatives get circled and sort of drawn as like we're dragging them outside of the circle. And we end up with the result, right, being 8 positives inside my circle. And the solution then is 8. And that gives a justification, either of these models give a good justification for how or why 5 minus negative 3 becomes 5 plus 3. Okay? So you don't get to use the fact that minus a negative is a positive when you're drawing these diagrams. That's not appropriate. All right? That's not appropriate. All right, we're going to do a couple other models. We've got the number line model and then the pattern model. All right, the number line model is a little bit awkward, but let me show you how it works. We have a number line. It starts at 0, and it moves us forward 5 because that's what this says. I'm moving 5 forwards. 1, 2, 3, 4, 5. And then here is what this language is telling me. The first negative tells me to turn around. And the second negative tells me to walk 3 backward. Now, I'm going to physically walk in front of you to show you this because it makes more sense than on the diagram or how it's going to show on the diagram. So let me physically walk it for you, and then we'll draw it the way that we would do it on the diagram. So I'm going to do the desks as though I'm walking forward. I did this last time, I know you guys know. So we're going to walk 5 forward. So we're going to walk 1, 2, 3, 4, and 5. And then it says I'm supposed to turn around and walk 3 backwards. But backwards would be that direction, the same direction I was already going, right? So then we walk another 1, 2, 3 backwards. I've run out of desks, so I can't walk any further through the wall. But I would be 8 from where I was started. Okay? So this is 5 over here. And then we actually end up walking 3 more in the same direction, and we don't have a very good describer in terms of how to draw this. I don't think I have anything detailed more on my paper. I don't. But you end up moving 3 backwards to here. That's my 8. It's not a very good 8, but it's an 8. I don't think it works as well as the other model for the number line, but it is still correct, and you can physically do it with your body and move around. It just doesn't have a good visual to draw it. Okay? All right, let's do the patterns one then. Patterns is the idea, we did this one before as well. We start out with something that we can actually subtract and stay within the whole numbers. So we'll just start with 5 minus 2. What is 5 minus 2? 3. And then we move on down. 5 minus 1 would be 4. 5 minus 0 would be 5. And then we subtract the number negative 1, which is the first sort of awkward place, right? It's the first place that we don't end up with whole number subtraction because I've got a negative 1 involved there. But what you do is, like we did in the last one, you look at this pattern. This pattern is increasing by 1. 3, 4, 5, what comes next? 6. 6 is the next number in the pattern. And then we go with 5 minus a negative 2. 3, 4, 5, 6. 7 is the next number in the pattern. 5 minus a negative 3. 3, 4, 5, 6, 7. 8 is the next number in the pattern. So that's using patterns and what you already knew about whole number subtraction to actually show what happens when you subtract a negative number. Okay? Okay, last example in this section, and not example, but last feature of this section. I think we've sort of talked about this in passing a couple of times, but we haven't done enough with it that it's actually been defined in your book. Order of operations. Have you seen PMDAS before? Has anybody used an acronym to describe it or to help you remember it? What have you heard?
Please excuse my dear Aunt Sally.
That's what I've heard too. Did anybody have a different one that they were presented with? Okay. Some people just remember it as Pemdas. That's good. Please excuse my dear Aunt Sally is a very common one. What it does is it describes the order of operations. However, there is an innate error or at least conceptual confusion in the way that it's presented. So let me show you that when we get there. What does P stand for in this? Not please, but I mean, what does it really mean? Parentheses. This tells us, and this is one of the inherent confusions, that we should do the parentheses first. But you have to understand what it means by do the parentheses. It means to simplify anything that's inside of parentheses. So it doesn't mean that we operate things to sort of transfer it inside the parentheses or combine it with things across the parentheses. It simply means work inside of the parentheses first. After you've simplified anything you can inside the parentheses, what would the E stand for? That is exponents. Now you'll notice the next one I did is I put MD and I put them together because the reality is it could be DM and it would be okay. It would be the same thing. There is not an ordering of D and M or M and D because the reality is they're the same thing. And the reality is you know that too, whether or not you've thought about it before. Multiplication by 2 is actually the same as division by 1/2. I mean, it has its counterpart that's equivalent. In fact, you've probably heard it described like this a little bit better. Division by 2 is the same as multiplication by 1/2, right? So multiplication and division go hand in hand. There is not an innate ordering for them. So if you've got multiplication and division in a problem, you simply work from left to right in the multiplication division. You don't do all the multiplication first and then all the division second. That is not appropriate. You just work from left to right. Okay. The last one, A and S, same thing. You could say SA and it would be okay, but it wouldn't sound so good, right? It wouldn't say, please excuse dear my Sally aunt. I don't think that's going to work as well. So, but maybe you come up with something much more creative. I don't know. So A and S, of course, stand for add and subtract, or addition and subtraction, right? So again, if there's multiple addition and subtractions going on in a problem, you don't do all the addition and then all the subtraction. You just work from left to right. Any addition or subtractions there are, you do the leftmost one moving towards the right as you go. Any questions? All right.